Let's do another example of implicit differentiation. And this is an excerpt from our textbook, which gives you like a little step-by-step guide for implicit differentiation, which I went through in the previous video. But basically, you're going to ddx both sides, take the derivative of both sides, or whatever variable you want to do. Then B, it says to apply the rules for differentiation. Basically, just solve your derivatives as they should be solved. And it, anytime an expression involving y is differentiated, dy dx will be a factor in the result. Essentially, that's by the chain rule. Whenever you're doing d dx of y, you need to have dy dx because that's what it is. Then step C, isolate all terms with dy dx on one side of the equation, factor it out, and divide whatever's left. I mean, again, this is exactly what we did over here. We differentiated both sides with respect to x because you can tell it's whatever variable is on your bottom of your differential. And then what we got is, we got some of the factors when we differentiated with respect to y, we had a dy dx at the end. When we did not, we just differentiated normally, end of story. We put all the dy dx terms on one side, we factored out because it was necessary, and divided by the rest to isolate dy dx. Exactly as it says to do here. So let's do another example. Say we're given a demand function, and a demand function often are written as like P's and Q's, which represent supply and demand based on X, the amount of objects being sold. But let's say we had a demand function, which is given by, it's also, if you've studied them before, you're probably used to the fact that they're not often written as functions. They're not represented as like P is equal to blah, 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 X. A lot of times they're written as X is equal to a factor of the demand or a factor of the supply. And let's say we wanted to know, well, what's the rate of change? What's the slope of the demand, even if it's not a function? And again, what you could do is you could just solve for P and then differentiate. That's fine. Or we could just differentiate implicitly, which again, since we're on the subject, let's go ahead and try that instead. But if you ever get stuck, you could just try it the other way. Solve for P, differentiate that way too. Oh, my dog smells trying to gas me out. But anyways, yeah, so let's go ahead and practice one more. So I need to take the derivative of both sides, and I want to do d dx here because the denominator of my derivative is dx, but it could be dp dq, df dj, whatever. The variables don't matter. It's going to work. Derivatives are going to work the same way regardless. But we try to be consistent, to not throw too many different things all at once. And also, if I'm, naturally the derivative of x is just 1, and again, those match up in their variables, so there's no need to pop out the extra expression. But on the right-hand side, I have this. And since it's in a square root, it might be helpful to rewrite it using a fraction. As we know, if we're going to try to differentiate such a function, it's going to be helpful to rewrite it using a fraction of 1/2, because that's the same thing as a square root, an exponent of 1/2. And now I could use the power rule because I have something to the 1/2 power. So I could drop the power, keep the inside the same, subtract 1, which give me -1/2. But as I know, I need to apply the chain rule in such instances when there's something else on the inside. So that's the derivative of x here, keep the inside the same. Now multiply by the derivative of the inside. So the derivative of 125 is 0, of course, because derivative of any constant is always 0. And the derivative of p cubed. Here is where, again, notice that I'm doing d dx of p. So I need to, as it says, dy dx will be a factor in the result, or whatever your variable is. In this case, it'll be dp dx, which is what I'm trying to find. But the derivative of negative p cubed is going to be -3p squared. And again, by the chain rule, I need to multiply by dp dx because it's obvious that p and x are dependent on one another because it's an equation. And so I can kind of imagine, like how I imagine it is there's like little x's in here that I don't know what they are. But at the end of the day, if you just remember to do this, you'll cover your bases. And since I'm trying to figure out dp dx here in the first place, obviously that's got to come from somewhere. So, it comes from that chain rule. And with implicit differentiation, I remember when I was learning calculus, I had no idea. It didn't make any sense to me at the time. But I remember the rule, and that's really all you got to do. Remember that this dp dx pops out, even if you don't really get why. Anyways, and now last but not least, I could clean up a lot of this stuff because I have 1 is equal to 1 over, well, again, this would be 2 times the square root of 125 minus p cubed, since that's a negative x1 and it's a half on the bottom. And then I would have a negative 3p squared on top. And that would be equal to times dp dx as well. So kind of combining some of these things together. But then I could, to solve for dp dx, I need to divide by all this. And to divide by a fraction, we could use the flip and multiply rule. I'd have dp dx is equal to, if I could multiply across by this and divide by this, but this would all end up giving me 2 times the square root of 125 minus p squared divided by negative 3p squared. So that's a cube. And that would give me my derivative function. Again, it's fine that it involves both p and x. In this case, it doesn't have an x at all, but that's fairly common. And again, if we wanted to, we could solve for p and plug it in, but not always necessary.